Greetings and welcome to Lesson 3.2, Independent and Mutually Exclusive Events. Don't skip this important step. Go through each of your new terminology for this lesson. If we have two events, we'll just call them Event A and Event B. They can either be independent or dependent. There's also a third type, and which is mutually exclusive. It's not the same thing as independent, and I'll talk about that more later. Two events are independent if one of these things is true. If you have the probability of A given B, if that equals the probability of A, they're independent. Or if this holds true, the probability of B given A equaling the probability of B, then again, they're independent. Or another circumstance that might be true is the probability of A and B. If that equals the probability of A times the probability of B, then the two events are independent. Otherwise, they're dependent. Now, a lot of the things that we're going to talk about are going to use rolling of the dice, usually a six-sided dice. If it's not stated how many sides, assume it has six. Flipping of the coin, then we only have heads or tails, or a deck of cards. Many of the problems that we will work with, we focus on using a deck of cards. We do this because most people are familiar with a deck of cards. So if you are familiar with a deck of cards, you know all the characteristics about a deck of cards, then you can click continue and move on. If you're not familiar with a deck of cards, just stay on this page and I'll describe everything I know about a deck of cards. A regular set of playing cards. The deck is made up of 52 cards that come in two different colors, red and black. Or a deck of cards. Many of the problems that we will work with, we focus on using a deck of cards. We do this because most people are familiar with a deck of cards. So if you are familiar with a deck of cards, you know all the characteristics about a deck of cards, then you can click continue and move on. If you're not familiar with a deck of cards, just stay on this page and I'll describe everything I know about a deck of cards. A regular set of playing cards. The deck is made up of 52 cards that come in two different colors, red and black. Half of the cards are red, half of the cards are black. So in numbers, that means 26 cards are red, 26 cards are black. It comes in four suits. The suits are the pictures, the little icons on the deck of cards. They come in heart, diamond, club, and spade. The hearts and diamonds are red, the clubs and spades are black. Each suit has 13 cards. So there are four suits which have 13 cards each. 4 times 13 is 52. The value on each card will range from 1 pip, that's the little icon on the card is called a pip, all the way up to a king. So it goes from a 1, other known as an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. So let me just summarize very quickly. There are 52 cards in a deck. The cards come in two different colors. There are 26 red cards, 26 black cards. There are four suits. Hearts, diamonds, clubs, and spades. Each suit has 13 cards. The cards' values range from a 1, also known as an ace, all the way up to a king. That's about all there is to know about a deck of cards. The possible outcomes of each event will depend on if you're using with replacement or without replacement. So think of a deck of cards. So you have well shuffled 52 cards consisting of 4 suits. Suits are clubs, heart, diamond, spade. We'll use the initial of each in this problem. So S for spade, H for hearts, D for diamonds, C for clubs. There are 13 cards of each suit, and the values consist of either a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. J for Jack, Q for Queen, K for King. Suppose that we sample 4 cards without replacement. Let's see which of these are possible outcomes. The first option is Queen of Spades, 1 of diamonds, 1 of clubs, Queen of diamonds. We've just pulled the first 4 cards from the top of the deck, and we haven't put them back in the deck. Is that possible? Think about it for a moment. The second choice is King of Hearts, 7 of diamond, 6 of diamond, King of Hearts. Now, just as a reminder, this is without replacement. I'm not putting the cards, once I pull it, back in the deck. Third option is Queen of Spades, 7 of diamond, 6 of diamond, and King of Spade. Which of these are possible? Well, certainly the first one is possible because none of the cards repeat. Because remember, once I pull the card, I don't put it back in the deck. The second option is not possible. I can't pull 2 King Hearts because there's only 1 in the deck. So once I pull it out the first time, it's not in the deck to pull again. So 2 is out. It is not possible. The third option, all those cards are different, and therefore that is possible. Then let's take that same scenario, but this time with replacement. Which of the following outcomes are possible? The outcomes listed are exactly the same as before. So let's say the first one was Queen of Spades, 1 of diamonds, 1 of clubs, Queen of diamonds. Is that possible if you replace the cards? And assuming each time you replace it, you shuffle it back up. The second one, King of Hearts, 7 of diamonds, 6 of diamond, King of Hearts. Is that possible? And the third one, Queen of Spades, 7 of diamonds, 6 of diamond, King of Spades. Is that possible? Actually, they are all possible with replacement. Because if you pull a Queen of Spades out, you put it back in the deck, you shuffle it. The next time around, you pulled out a 1 or ace of diamonds. You put that back in the deck, you shuffle it. Next card you pull, an ace of clubs. Put it back in, shuffle it, and you pull out a Queen of diamonds. That's all totally possible. For the second one, the first time you pull a card, you get a King of Hearts. You put it back in the deck and you shuffle it. The second time you pull a 7 of diamonds. You put that back in the deck and shuffle it. Third card you pull is a 6 of diamonds. That's okay. Put it back in the deck, shuffle it. The fourth time, you pull the King of Hearts. Again, that's totally possible because remember, you replaced it. You put it back in the deck. So all 3 are possible. So possible outcomes are going to be dependent with replacement or without replacement. Mutually exclusive is not the same thing as being independent. If you have 2 sets, A and B, and those 2 sets are mutually exclusive, then the events do not occur at the same time. They just don't have any crossover. They don't share any outcomes in common. And therefore, the probability of A and B, meaning that thing that they share in common, well, there is nothing that they share in common, so that probability of 0. Suppose the sample space S exists and it is 1 through 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let the event A be 1, 2, 3, 4, 5. Let event B be 4, 5, 6, 7, and 8. And let C be 7 and 9. What would the set of A and B look like? If it's A and B, it means it's everything that they share in common, and therefore the set would be 4, 5. Well, what's the probability of A and B? Since the set of A and B contains 2 items and it came from the sample space that had 10, it means that the probability of A and B is 2/10. what does the set A and C look like? Well, A is 1, 2, 3, 4, 5, and C is 7 and 9. They share nothing in common, and therefore the set A and C is the empty set. The empty set symbol looks like a circle with a line drawn through it, similar to the not symbol. What would be the probability of A and C? Well, if there's nothing in the set, then the probability is 0. Not nothing, but 0. What does the set B and C look like? B is 4, 5, 6, 7, 8, and C is 7 and 9, so it's what they have in common. So the set B and C looks like the set 7. What's the probability of B and C? That would be 1 out of the sample space of 10. In other words, 0.1 or 1/10, however you want to look at it. Here's an example we can work through. We have an experiment. We flip 2 fair coins. The sample space is going to be, remember these are separate coins, so the first coin could be a head, the second coin could be a head. The first coin could have been a head, the second coin could have been a tail. The first coin could have been a tail, and the second coin could have been a head, and then the first coin could have been a tail, and the second could have been a tail as well. So we'll use H's as heads, T as tails. Let us assume that we have an event, A, and the event is getting at most 1 tail. If we are at most 1 tail, we could get 1 tail or no tail. But as soon as we do 2 tails, then we broke our event. So the event of getting at most 1 tail, we're looking for the possibility of no tails or 1 tail. The set would look like HH, that's getting no tail, or HT, or TH. Now you might think that HT and TH are the same thing, but remember we're flipping 2 different coins. So it is a very different event to flip a head first, then a tail, versus a tail first, then a head. They're 2 separate outcomes. So our A would have a set of 3 values. The probability that A occurs is 3/4 because our sample space has 4 possible outcomes and the set A has possibility of 3 outcomes, and therefore our probability is 3/4 or 0.75. You really should get used to doing decimals where possible. Let event B be the event of getting all tails. That means both coins must be a tail. Well, we only have 1 outcome that's possible. The first is a tail and the second coin is a tail. Therefore, the set B has 1 outcome of TT. What's the probability of B? Well, it has 1 out of the 4 possible out of our sample space. Therefore, its probability is 1/4 or 0.25. Let's have another event, C, and let's let that event be getting all heads. That means no tails at all. That means the first coin has to be a head and the second coin has to be a head. And therefore, its set looks like HH. What's the probability of C occurring? Well, that's 1 outcome for the 4 possible that we have. So again, it's 1/4, 0.25. Let's have another event happen, D. Event of getting more than 1 tail. If we're more than 1 tail, then we could be 2 or 3 or 4 or 5 or 6 or 7, but we're only flipping 2 coins. So the possibility is only both of them being tails. D has the set of TT. So what's the probability of D? Well, 1 out of the 4. It has 1 in its set out of the 4 possible outcomes, so 1/4. E is the event of getting a head on the first flip. Therefore, we could flip a head or a head tail. Those are both possible outcomes. Therefore, the probability of E would be 2 outcomes out of the 4, and therefore 0.5 or 0.50. F is the event of getting at least 1 tail in 2 flips. That means in either of the flips, we could have gotten a tail. But it doesn't rule out having both of them be tails. So that's actually, we could get a head-tail, a tail-head, or a tail-tail, because we need just at least one tail. Didn't say that both of them couldn't be tails. And therefore, it could be HT, TH, and TT. The probability of F would be 3 out of 4, so 3/4, or 0.75. When you look at what each event can have as outcomes, you'll notice a few things. B is mutually exclusive to A, C, and E. They don't share anything in common. Now, I'm not saying that A, C, and E don't share anything. I'm saying that A, C, and E don't share anything with B. Likewise, A, C, and E don't share anything with D, so they are mutually exclusive to D. And C is mutually exclusive to B, D, and F, since they don't share anything in common. You've reached the end of this lesson.